right, so this is the second example from the beam bending skeleton notes on beam bending. So we have this beam and it has equal bending moments on each side of this beam of 45 kip feet. The cross-sectional dimensions are labeled on the cross-section, and we're supposed to find the centroid location and the moment of inertia about Z for part A. And then for part B, we're supposed to find the maximum bending stress produced in the cross-section and state whether the stress is in tension or compression. Okay, so we're going to start with part A, the centroid and the moment of inertia, and the way we do that is we make our tables. So for the centroid, part A, centroid, we have y bar equals the sum of the yi's, so the centroids of the individual parts, times the area of each part, all over the sum of the areas of the different parts. So we're going to break this one up into 3 parts. So we will have, I'm going to start at the top, and we're going to have part, can't see that. We're going to have part 1, part 2, and part 3. Okay, so then we make our table. First column, part number. Second column, the centroid. So we have 1, 2, and 3. Then we need the centroid of each part. We are going to use we're going to find the centroid going up from this line. So y goes up. Okay, so then, so of part 1, we have to go up through the first, through part 3, that's 2 inches. Up through part 2, that's 6 inches, and then halfway up part 1, which is 1.5 over 2. So we have up 2 inches plus the 6 inches of part 2 plus halfway up part 1, 1.5 over 2, and we get 8.75. Part 2. Now we just have to go up through part 3 and then halfway up part 2. So part 3 is 2 inches plus the whole height of part 2 is 6 inches over 2, and that equals 5 inches. And then part 3, all we have to do is go halfway up part 3, which is 2 over 1, and we get, it's 2 over 2. 2 divided by 2 equals 1. All right. So that's that column. Then we need the area of each column, or each part, and that'll be in inches squared. So part 1 is 7.5 inches times 1.5 inches, and we get 11.25 inches squared. Part 2 is 0.75 inches wide times 6 inches tall. We get 4.5 inches squared. And then part 3 is 3 inches wide times 2 inches tall. We get 6 inches squared. These we sum up. So the sum of all of these is the areas is 21.75 inches squared. That'll be our denominator. All right, then we find yi times ai, so column 2 times column 3, and these are going to be inches cubed. So we're going to get 98.4, and then we'll get 22.5, and then we'll get 6. And we sum all of these up so that we have a numerator. So we get 126.9. Then we plug it into this equation. We get y bar equals 126.9 inches cubed all over 21.75 inches squared, and we get y bar equals 5.8 inches from the bottom. So if we have this, our centroid is going to be somewhere around 8.5. It's going to be over halfway, about. So it'll be right here. They have it marked for us. And that distance is 5.8 inches from the bottom. So y bar from bottom. Okay, so then if we calculated, we'll do that later, y from the top. Okay, so now we're going to do the moment of inertia. And here we use the parallel axis theorem. So we're going to make another table. So same 3 parts. Part 1, 2, and 3. We need the moment of inertia of each part about its own centroid. That's I bar. That'll be in inches to the 4th. The moment of inertia was parallel axis theorem. Okay, so we have part 3. B is 7.5 inches. H is 1.5 inches, and that value we cube all over 12, and we get 2.11 inches to the 4th. Then part 2, the base is 0.75 inches, the height 6 inches, that's cubed all over 12, and we get 13.5 inches to the 4th. Okay, and then part 3, the base is 3 inches. The height is 2 inches. Cube that, divide it all by 12, and we get 2 inches to the 4th. Okay, so we have the areas up above. Now we need to find the distance, d, in between the centroid of the whole part and the centroid of the part of the individual parts. So the centroid of the whole part is 5.8, the sign doesn't matter, minus the centroid of part 1, we can just look up here, is 8.75. So we can do minus 8.75, forget the sign, and we get 2.95. We're going to square it, so the sign doesn't really matter. Okay, then, again, centroid is 5.8 of the whole thing. The centroid of part 2 is 5. So then we get 0.8 is D2. And then, again, centroid of the whole part is 5.8. Minus the centroid of part 3 is 1. And so we get 4.8. Okay, now we multiply a times d squared. So we get inches to the 4th. We get 67.5, 2.9, and 138.2. All right, and then lastly is we add 1 and 3 together. So we get IZ is the sum of all of those. So we get 2.11 plus 67.5 equals 69.6. Then we have 13.5 plus 2.9, and we get 16.4. And then we have 2 plus 138.2, and we get 140.2. We add all those together, and the sum of those is IZ. So this was the centroid, and IZ equals 226.2 inches to the 4th. Alright, so that's part A. Now part B is the maximum stress in this beam and state whether it's in compression or tension. So if we have Y from the bottom, then we need Y from the top so we can figure out what is the bigger difference. So the total Y, we could take 2 plus 6 plus 1.5 minus 5.8 and we get 3.7 inches. So this would be y from top. Okay, so our equation for the stress equals negative my over I. Max stress at largest y. So the max will always occur on either the top of the beam or the bottom of the beam. If it's not symmetrical, then it's whichever is farthest away from the centroid. In that case, it will be the bottom of the beam. This beam has a positive bending moment, so it's going to be in tension. Okay, but we can also just follow our sign convention, and that will tell us that it's in tension. So we're going to use y bottom equals 5.8 inches. It is negative because it's below the neutral axis. Okay, so then we just plug in everything we know. Sigma max equals negative. The moment is 45 kip feet and it's positive. 45 kip feet, we're going to change that to inches. 12 inches per foot times y of negative 5.8 inches all over I of 226.2 inches to the fourth. And we get sigma max equals 13.8 KSI. The negatives cancel. We get a positive, and it's in tension. We also know if we put a positive moment, we're going to get tension on the bottom and compression on the top.